Today, velocity as a vector. So one of the applications we did yesterday was force, and it had some challenges in it. And I really hope you went through the homework carefully because there's very many different types of questions, and getting used to all those different situations is a big challenge. Today, velocity, which is number 2 on the big application charts of things that this vector mathematics is used on. So we have seen that vectors can be used effectively to represent forces. Another useful application is velocity. When a vector is used to represent velocity, the magnitude of the vector represents the speed, and the direction of the vector represents the direction of motion. Pretty obvious there, I think, about how we would use velocity as a vector. 2 specific applications that we'll start off with is boats and aircrafts. So when a boat or aircraft is steered toward a specific direction, that direction is called the heading. So when you have trouble with heading, come back to these few sentences. The direction you're trying to go is the heading. That's where your airplane is pointed. And you think to yourself, well, isn't that the way I'll go then? No, if there's a wind, the wind's going to pull you off course. So even though you're trying to head, say, straight north, if the wind is blowing east, you're not going to end up going north. So your heading is where you are headed, where you're trying to go. The direction is measured by now, when you measure heading, the actual real-life version of this, they always give the heading clockwise from north. I know that's not the same as what we're used to doing. We're used to doing counterclockwise from the x-axis. And that's the difference between doing math versions of problems and the real-life version of what pilots and captains of boats actually do. They always measure heading clockwise from north. There's a lot of great reasons why there's a difference in how these things are done. But for now, all you have to know is this is the way it is done. If you want to fly an airplane, you always measure your angle clockwise from north. So when a plane flies, its velocity relative to the ground is the resultant, okay, important little tidbit there, let's get my highlighter out, is the resultant of the plane's velocity through still air plus the velocity of the wind. So right off the hop here, basically all we're going to do is you put the velocity of the plane through still air, and then you add to that, tip to tail, the velocity of the wind, and the resultant you get when you add those 2 vectors will be the resultant velocity of the plane, where it actually goes to. And similarly for a boat, the actual velocity relative to the shore is the resultant of the boat's velocity in still water plus the velocity of the current. And again, to make that clear, let's say you're trying to go straight north in the water, but the current's going straight east, then you're not going to go straight north. You're going to be pulled off course. A couple of examples, and let me give you my biggest hint. The most important thing I can say in all these things is when you draw these pictures, draw them big, especially when the angles get crazy. There's 2 different examples here, one with crazy angles and one with really easy angles. Really easy angles, you can draw small pictures if you want, but as soon as the angles get crazy, you need a really big picture if you're going to be able to figure out what angles to use. Now, this plane leaves the airport flying on a head of 55 degrees, and that 55 is 55 degrees off of north. So here comes my picture. Here's what the plane's trying to do. It's trying to go 55. I'm going to draw it right about there. And just a little, this is a really good trick. Let's just do a little dotted line straight north, and all you're doing there is establishing what angle we're headed at, because my diagram's not meant to be drawn to scale, it's just meant to give me the idea here. These little dotted lines that you draw either will be north, east, south, or west, just a straight line in one direction, and I'm just going to put down here this angle in here, which is 55, and that's right in here, 55. That's the angle with north. Now the wind is blowing 30 degrees north, 30 degrees east. Now that's a weird symbol as well, used all the time for directions when you're actually doing them in the real world. And what that means is start at north, but then go 30 degrees east from that. So I'm just going to do a little diagram over here. So if that's north and that's east, maybe you need a little acronym. Maybe you don't know your north, east, south, and west. The one I know is never eat shredded wheat. Now, that's an out-of-date acronym because I don't know if I've even seen shredded wheat around in the stores. It's an old cereal. But that's the one I know. You can make up your own acronym for knowing which way north, east, south, and west are. But in this case, they said start at north and then go 30 degrees east. So this wind is sort of in there. It's had 30 degrees towards east. It started at north, but then it headed this way, 30 degrees east. So when I draw it on my diagram here, I've got to add on this wind. So there's the velocity of the plane, but then the velocity of the wind will be something like this. And I'm going to draw a little north on there. I don't like how I did that, so I'm just going to get rid of that north. Oh, it's going to make me do it all the way across. Okay, very, very tiny in here. And that's a 30 degrees in there. Can I zoom? Oh, it could zoom, but can't zoom in right. Microsoft Word isn't great on that. So there's the velocity of the plane relative to the ground. So plane to ground. And this is the relative of the air. And so my resultant velocity, I'm going to draw it in red. And maybe I'll just draw it a little bigger so we're clear on what it is. The end velocity is, the resultant velocity is like that. Straight lines if you can. So we're in great shape because when you look at this, I hope you immediately start thinking of cosine law. And the reason I'm thinking of cosine law is I know the velocity of the plane relative to the ground. And that's 400 kilometers an hour. Sorry, this is velocity of plane relative to the air. That's 400 kilometers an hour, and the velocity of the air is 35 kilometers per hour. And so I have those two sides, and I'm really thinking about cosine law here, so I'm going to label this as C. This is what I really want, is the ground speed, how fast this thing's actually moving, and I'll do the direction afterwards, but I need this ground speed first. And I'm very close to getting it, but you'll see I don't have this whole angle I need inside the triangle opposite to the C there. But I've got this 30 here, and now I'm just going to draw, continue on that dotted line straight down, and I hope you can see the C pattern. I'm going to do the C pattern here with a highlighter, and then I'm going to erase it. Small pen, highlighter. There's the Z pattern. The Z pattern almost always comes up in these questions if you draw these little fake north-south lines on there. So that's all there. And so down in here, this is 55 degrees. And you can see this is the bare minimum size. I mean, it's as big as I was able to draw it on here, and maybe I should have gone bigger, but it's the bare minimum size you want these diagrams to be able to figure out these angles. And so what I know then is if that's a 55 in there, then that in there is a 35. Now I've got that whole angle. I don't know if you can see that whole angle I need here. It's going to be all the way from here to here. It's got a 55. It's got a 90. Sorry, it's got a 35, a 90, and a 30. So that's a whole angle of 155 degrees. Now that is the exact thinking that makes these questions difficult, is drawing all those angles on there. And a big, big picture is what you need to get all that done. Because once you get there, finding the actual ground speed is no big deal. It's just a little cosine law here. And so I get C squared equals, I'm going to use a 400 squared plus 35 squared minus 2 times 400 times 35 times cosine of 155. All that work to get that angle there. And when I get that, I get C squared equals, let's type it in here, I get 186601.618. Maybe you don't even put that step in there. Maybe you square root that all in one step. Try typing in your calculator, and I get 431.2. I'm going to round it to the nearest whole number there. The other velocities were whole numbers, so my resultant velocity, I'll do 431 kilometers per hour. Okay, so pretty simple application of cosine law, except for drawing these pictures. And I won't tell you that the pictures are easy. They're not. You got to do a lot of careful drawing out to do these things. But draw them big and get these little dotted norths and souths and east and west on there to help you reference and help you create your Z patterns, because it's almost always going to be Z pattern that comes out of here. Now, the question is, what direction is this heading in? And so what I'm going to find out is this angle in here using sine law. So what I'm going to do is I'm going to call that angle A. And angle A really represents how much this plane was pulled off course, because this black line was the line of where it was trying to go, and this red line represents where it ended up going, and so this A is how much off course it was pulled. So I'm going to do sine A over 35 equals sine 155 over the 431.2 I just solved for. So you can see 431 I just solved for. You can see why I did that first, why I found the C first, because then I could do this angle. So after some rearranging, I'm going to have to do the sine inverse of 431, or whoops, of 35 sine 155 over 431. And I'm doing the sine inverse of that big mess. Punch that in my calculator and I find 2 degrees is how much this was thrown off course. So therefore, the ground speed is 431 kilometers per hour at a heading of, I'm going to say 053 degrees. It was 055 degrees was where they tried to go, but they were pulled 2 degrees back towards north there, and so I got a heading of 053. Second example, much simpler setup. In fact, we did a similar one to this last chapter. A canoeist who can paddle at a speed of 5 kilometers an hour in still water wishes to cross a river 400 meters wide that has a current of 2 kilometers an hour. If he steers the canoe in the direction perpendicular to the current, determine the resultant velocity. Find the point on the opposite bank where the canoe touches. Well, I'm going to call that part B, and I'll get to part B in just a second. For now, part A. So what he's doing is his velocity, he's trying to go straight across the river like this. He's trying to go, ooh. That's him paddling across the river at 5 kilometers per hour. But meanwhile, the current is trying to pull him down this way at 2 kilometers per hour. You see, to get the resultant velocity, I add his velocity that he's trying to go across the river at to the amount that the current's pulling him off course. And so what I get is this, and actually a very straightforward application of all this here, except for the part B here. So for part A, I can just use Pythagorean Theorem. His resultant velocity, I'm going to go back to using a little bit better symbols here for these type of questions. His size of his resultant velocity will be 5 squared plus 2 squared. And so I get root 29. His resultant velocity, the size of it will be 5.4 kilometers per hour. Determine the resultant velocity. So if it wants resultant velocity, I've found the resultant speed, but to get that angle, I'll also need this angle here, which I'll label A. And so to get that A, I got to do tan inverse of 2 over 5. And so I get this angle to be, I do tan inverse of 2 over 5, I get 22 degrees. Okay? So that's the resultant velocity for the canoe. I labeled it part B, which was to find the point in the opposite bank where the canoe touches. Well, a little bit of physics here. You physics people will break this into X and Y components, and that's fine. And this question maybe demands that. But just a little straightforward think here is I'm just going to go, okay, time to cross. First, I'm going to say time to cross the river. And we just need one little physics equation here. And my physics equation here is velocity equals distance over time. So I'm going to rearrange that to get an equation for what I want, which is how much time does it take to cross. And to get that time, I take the distance and divide it by the velocity. The distance here is 0.4 kilometers. The velocity is 5. And so his time to cross is 0.08 hours. That's not 8 minutes. It's 0.08 hours in decimal form. And then once I have that, I can get my distance down the river. And for that one, what I need is still the same equation, but I'm just going to rearrange it differently. I'm going to go distance equals velocity times time. So the distance equals the velocity, which is 2 kilometers an hour, times the time, which is 0.08 hours. 08 hours. And so I get distance equals 0.16 kilometers down the river. So if he really was trying to go straight across the river and make it to a point right there, if that's where he was trying to get to, he has been pulled down the river by 0.16 kilometers by all this. Okay, I need to warn you. There's some homework questions that where you have to solve for the velocity of the river or the velocity of the air, and so setting up the diagrams is a lot more difficult, but you got to try a few first. So take a run at this. Don't look at this and go, even if you're a physics person, don't look at this and go, oh yeah, I got that, and just ignore this homework, because it will come up and bite you, folks. Take some time, draw big diagrams, and in the case of headings and so on, draw those dotted lines on there to help you draw those diagrams out and get those angles. That's all for today. Try out that homework. Have a great day.